They are the great dark spots of the universe, not merely black holes, but enormous black holes, billions of times the mass of our sun. They are everywhere we look, even looming distantly out of the light of the cosmic dawn. Supermassive black holes have all the space-warping strangeness of their smaller kin, which we see dotted about our galaxy. They too swallow all matter, light, and cries for help. But they hold another level of mystery. We know that small black holes with a mass a few times that of the sun are born when a large star's heart collapses in a supernova, but nobody can explain the genesis of the giants. Scientists call it one of the major problems in modern astronomy. As renowned theoretical physicist Michio Kaku said, "There is a Nobel Prize waiting for the enterprising individual who can solve this problem." What's interesting is that we now have a potential candidate for that prestigious award. The James Webb Space Telescope is shaking up astronomy by spotting a bunch of giant black holes all over the early universe. And scientists just say that this stunning discovery could solve the long-standing puzzle of the first supermassive black holes. Join us as we dig deep into how James Webb just cracked the universe's code. When it comes to the science of cosmology, the history of the universe, and how it came to be the way it is today, one of the crowning achievements of the past 100 years is the development of a standard model of cosmology. The dominant factor in determining how the universe evolves is gravitation, which is governed by general relativity, and accounts for the expanding universe, as well as the assembly of large-scale cosmic structures. The contents of the universe have been determined to be dark energy, dark matter, normal matter, neutrinos, and photons. And the universe as we know it began some 13.8 billion years ago with an event known as the Hot Big Bang, with density imperfections seeded by a preceding phase known as cosmic inflation. Despite all the observational evidence we have supporting this picture, it may not be fully correct. Each time we observe the universe in a new way, we have to check that what we're seeing is still consistent with this model. With the recent addition of James Webb to the arsenal of tools astronomers have, is this picture in trouble? That's what many, including Patreon supporter Chad Marler, want to know. The newest fad among armchair physicists is that the Webb observations of galaxies that are more mature than expected in far reaches of the universe disproves the Big Bang. I'm not sure there has been enough time or data accrued to actually make a real account of the results yet, but I sure haven't heard anyone with any credentials say that either. Certainly, a lot of extraordinary claims have been made, but what's the full truth? Here's the current status. The first thing we have to do is lay out, based on our picture of the universe, how we expect events to unfold in our universe. This picture, sometimes called the standard model of cosmology, sometimes called the inflationary hot Big Bang, and sometimes called the lambda cold dark matter model, has been remarkably successful, explaining features ranging from the internal motions of individual galaxies, the motions of galaxies relative to one another, the motions of galaxies within groups and clusters of galaxies, weak and strong gravitational lensing on all cosmic scales, the structure and growth of the cosmic web, and the features found in the Big Bang's leftover glow, the cosmic microwave background. It also predicts that, as we look farther and farther back in time, i.e., to greater and greater cosmic distances, that the galaxies we see will be inherently smaller, bluer, less evolved, less rich in heavy elements, and that at some point beyond where we've been able to look, we should cease to see stars or galaxies of any type as we'll reach the universe's dark ages. But that's simply a picture of what happens. What we need, if we want to compare theory to observations, is to quantitatively figure out not just what happens, but when it happens, and quantitatively, how much it happens by. Even though the laws of physics are well known, and the starting point, or our initial conditions, are also well known, our best quantitative predictions still come along with a large amount of uncertainty. From the theory of cosmic inflation and the patterns of fluctuations that we see in the cosmic microwave background, We know that our universe began at the start of the hot Big Bang from an almost perfectly uniform state. There were the seeds of structure, density imperfections, imprinted atop that near-uniform background, leading to underdensities and overdensities at about the 1 part in 30,000 level, that were almost but not quite the same on all cosmic scales, about 3% larger on size of the universe scales than on size of a galaxy scales. We know that early on, these imperfections grew gravitationally, but also had to contend with interactions with and pressure from radiation, like photons, creating a pattern of peaks and valleys in how overdense, underdense various regions were on a variety of cosmic scales. Then, the universe forms neutral atoms about 380,000 years after the hot Big Bang and expands, cools, and gravitates according to the laws of general relativity. As long as these density imperfections remain small compared to the average density of the universe, it's easy and straightforward to compute how they grow. But as they grow larger, a series of effects all come into play, making the question of how big do they grow and how quickly very assumption-dependent. For example, as large amounts of gas begin to accrue in these overdense regions, how efficiently does that gas cool? As these overdense regions grow within the expanding universe, with some small-scale regions superimposed atop larger-scale overdensities, how do these high-density regions interact in these overlapping locations? Some overdense regions will occur close to other overdense regions. How is the growth of structure affected when these regions interact? As normal matter accumulates in the centers of these overdense regions, it slows down, collides, and heats up. As that heat gets radiated away, how does that feedback affect the growth rate of these regions, including both the normal matter and the dark matter? And finally, when stars finally form in these very different environments to the ones we find today, how long do they live? How do they die? How does that impact the normal and dark matter that doesn't become stars? And what implications does that have for subsequent generations of stars and the growth of these early cosmic structures? It's important to understand that the answers to all of these questions are uncertain. They're firmly in the realm of the purely theoretical and are dependent on what details we include and exclude in our models and simulations. Are we using the correct models to identify halos, where a halo represents an individual overdensity in space? Or are we incorrectly treating interdependent halos as independent entities or vice versa? Are we modeling the first stars correctly, including their initial mass functions and their death throes? Or are they heavier and more likely to directly collapse to black holes than we think? For that matter, do we even need stars to form black holes? Or can these intersecting, inflowing streams of gas form the seeds of supermassive black holes directly, possibly with masses that are millions of times the mass of our Sun right away? It's pretty clear that the very first objects, stars, black holes, and star clusters, begin forming no later than about 150 million years after the Big Bang, and perhaps as early as only 50 to 100 million years after the Big Bang. But these ought to be relatively rare occurrences. But now, for the first time, owing to the unprecedented capabilities of the James Webb Space Telescope, we're beginning to discover and characterize unpredicted ancient objects found in these very, very early stages of our cosmic history. In other words, the telescope was already reshaping astronomers' understanding of the cosmos's first billion years. One set of enigmatic objects stood out in the myriad presentations. Some astronomers called them hidden little monsters. To others, they were little red dots. But whatever their name, the data was clear. When James Webb stares at young galaxies, which appear as mere red specks in the darkness, it sees a surprising number with cyclones churning in their centers. As Christina Eilers, an astronomer at Massachusetts Institute of Technology, said, "There seems to be an abundant population of sources we didn't know about, which we didn't anticipate finding at all." In recent months, a torrent of observations of the cosmic smudges has delighted and confounded astronomers. Everybody is talking about these little red dots. said Xiaohui Fan, a researcher at the University of Arizona who has spent his career searching for distant objects in the early universe. The most straightforward explanation for the tornado-hearted galaxies is that large black holes weighing millions of suns are whipping the gas clouds into a frenzy. That finding is both expected and perplexing. It is expected because James Webb was built, in part, to find the ancient objects. They are the ancestors of billion-sun behemoth black holes that seem to appear in the cosmic record inexplicably early. By studying these precursor black holes, scientists hope to learn where the first humongous black holes came from and perhaps identify which of two competing theories better describes their formation. Did they grow extremely rapidly, or were they simply born big? Yet the observations are also perplexing because few astronomers expected James Webb to find so many young, hungry black holes, and surveys are turning them up by the dozen. In the process of attempting to solve the former mystery, astronomers have uncovered a throng of bulky black holes that may rewrite established theories of stars, galaxies, and more. As Marta Voluntari, an astrophysicist specializing in black holes at the Paris Institute of Astrophysics, Voluntari and her colleagues are now contending with the influx of giant black holes in the early cosmos, said, if they are real, they completely change the picture. In the recent past, many ideas have been floated to solve the puzzle, but they all fall into three categories. Perhaps we've got the seed size and time right, but the growth wrong, and that black holes' masses grow faster than we realize. Perhaps we have the seed size all wrong, and that larger cosmic seeds are possible, driven by processes like structural formation or a much greater initial mass for the heaviest stars. Or perhaps our picture is way off base, and the universe was actually born with black holes that formed before any stars ever could, a set of primordial black holes. For the first option, it's true that non-spherical accretion can cause black holes to grow faster than the Eddington limit, but that type of accretion struggles to persist for long periods of time. Even if we allow for bursts of faster-than-expected growth, it remains very difficult to explain how so many supermassive black holes, as there are now some 200 of them discovered at very early cosmic times, all experienced what should be rare and transient conditions for such persistent epochs. For the third option, this starts off as a remarkably unattractive proposition. We'd have to postulate some new, never-before-seen physics to create a spike in the mass spectrum at a particular value. In order to make a primordial black hole, you need to have a region of space that's more dense than 168% of the cosmic average in the early stages of the expanding universe. But remember, we just said that about 100% of all early regions in space are between 99.988% and 100.012% of the average density. Unless you invent some new way to have ultra-large magnitude fluctuations on a very small and specific cosmic scale, and no other, this scenario cannot come to pass. However, there's still a hope that this problem, or rather, this apparent problem, may simply turn out to result from ordinary, mundane, run-of-the-mill astrophysics. Sure, a seed black hole of a few hundred solar masses at an epoch of 100 million years after the Big Bang won't quite do the job. But if we could make seed black holes that were just 100 times more massive at that same early epoch, that would provide a way out. If the universe could give birth to a seed black hole that was a few tens of thousands of solar masses just 100 million years after the Big Bang, that would resolve the tension. The composition of the universe, back before the very first stars ever formed, provides a tremendous clue that this might be possible. Today, stars form from the collapse of gas clouds, made mostly of hydrogen and helium, but peppered with a small amount of heavier elements: oxygen, carbon, nitrogen, neon, silicon, sulfur, calcium, magnesium, and iron, among others. It's primarily those heavy elements that allow those gas clouds to cool and collapse, giving rise to stars with an average mass of 40% that of the Sun. Sure, We might be able to form a few very massive stars with masses of 50, 100, or even 200 solar masses or more, but just a tiny fraction of them will be massive enough to go supernova and/or leave a black hole remnant behind. However, early on, star formation would have had to proceed differently. Without any of those heavy elements present, the most efficient way to cool clouds of gas that are attempting to gravitationally contract is still tremendously inefficient. To have neutral molecular hydrogen radiate that heat away. With such an inefficient means of cooling at play, molecular clouds have to get much more massive in order to collapse, and the expected stars they'll form are 25 times more massive than today's stars, on average. It might be quite common to form stars of many hundreds or even a few thousand solar masses in these very early stages, and those stars might not even go supernova. It's plausible that they'll directly collapse, leading to a scenario where 100% of the star's mass becomes a black hole. Given that, we've seen stars directly collapse. In the environments where the most massive stars reside, we find many stars of comparably high masses, and that the first stars formed from ultra-massive molecular clouds with, likely, many stars of 1/1000 solar masses. It seems reasonable that perhaps many seed black holes cloud form, and those seeds could then merge together, leading to a starting black hole that just might, potentially, start off with enough mass for us to wiggle our way out. But even this scenario, which gets us quite a bit closer to the desired outcome, poses a difficulty. How do we get these seed black holes to all merge together quickly enough without gravitational interactions, either forcing an ejection or mutual interactions, clearing out the galactic center from the needed material for accretion? There needs to be something else. Something else has to come into play if we're to transform this conundrum from relying on hand-waving to relying on solidly understood physics and astrophysics. And that's precisely where the new study, led by Daniel Whalen of the University of Portsmouth, comes in. By simulating how structure forms in the early universe, including dark matter, early star clusters, and streams of neutral gas, i.e. normal matter, and watching how proto-galaxies and star clusters merge together amidst the backdrop of the emerging cosmic web, cosmologists can monitor where large, massive collections of matter can gather in one particular location. A few years ago, this method was able to reveal that cold, ultramassive streams of gas would collide at the nexus points of this proto-cosmic web, and that gas could rise to high densities in small volumes, containing as much as 100,000 solar masses in one particular location. But these environments are rare and cannot explain the U-200+ very massive quasars we've discovered back when the universe was just 5% of its current age or so. That's where the new simulations by the Portsmouth group comes in. The team was able to show that where strong, cold accretion flows occur and converge, they can all of a sudden trigger the all-at-once collapse of dense clouds of normal matter, creating either short-lived stars or direct collapse black holes that range from 30,000 to 40,000 solar masses. As the simulation snippet illustrates, there's no need for any fine-tuning mechanisms to trigger this phenomenon, whereas previous studies invoked ultraviolet backgrounds, supersonic streaming motions, or some variety of atomic and molecular cooling. This new research showed that these cold gas flows lead to a copious amount of turbulence, which prevents star formation from occurring entirely until a critical mass is reached. Upon crossing that mass threshold, however, the dense region suddenly collapses, which can trigger the formation of individual objects, stars or black holes, of up to 40,000 solar masses. For the first time, using known non-exotic physics alone, a team has successfully shown that seed black holes of the needed mass can be created just slightly over 100 million years after the Big Bang. This theoretical development couldn't come at a better time, right as James Webb's science operations are exceeding all expectations. One of its unprecedented capabilities will be to examine the earliest black holes in their galactic environments, shedding light as to how they formed and grew up. This novel scenario, where cold gas streams collide to produce monster-sized stars that can quickly form black holes up to tens of thousands of solar masses, will soon be put to the ultimate test. As Whalen himself noted, the only primordial clouds that could form a quasar just after cosmic dawn, when the first stars in the universe formed, also conveniently created their own massive seeds. This simple, beautiful result not only explains the origin of the first quasars, but also their demographics, their numbers at early times. The first supermassive black holes were simply a natural consequence of structure formation in cold, dark matter cosmologies, children of the cosmic web. For nearly 2 full decades, astronomers have puzzled over just how these supermassive black holes, found in the universe's most distant quasars, grew up to be so big so fast. This new result strongly supports a novel, gas-driven scenario that requires no new physics. In the next few years, and perhaps even the next few months, we'll get to find out precisely how the universe's most massive, early objects grew up. As a awe-inspiring information, 2 powerful telescopes, James Webb and Hubble, has just combined to create most colorful view of universe. They have united to study an expansive galaxy cluster known as MACS 0416. The resulting panchromatic image combines visible and infrared light to assemble one of the most comprehensive views of the universe ever taken. Located about 4.3 billion light-years from Earth, MACS 0416 is a pair of colliding galaxy clusters that will eventually combine to form an even bigger cluster. The image reveals a wealth of details that are only possible to capture by combining the power of both space telescopes. It includes a bounty of galaxies outside the cluster and a sprinkling of sources that vary over time, likely due to gravitational lensing, the distortion and amplification of light from distant background sources. This cluster was the first of a set of unprecedented, super-deep views of the universe from an ambitious, collaborative Hubble program called the Frontier Fields, inaugurated in 2014. Hubble pioneered the search for some of the intrinsically faintest and youngest galaxies ever detected. Webb's infrared view significantly bolsters this deep look by going even farther into the early universe with its infrared vision. We are building on Hubble's legacy by pushing to greater distances and fainter objects, said Rogier Windhorst of Arizona State University, principal investigator of the PEARLS program, Prime Extragalactic Areas for Reionization and Lensing Science, which took the Webb observations. While the new Webb observations contribute to this aesthetic view, they were taken for a specific scientific purpose. The research team combined their 3 epochs of observations, each taken weeks apart, with a 4th epoch from the Canadian Nearest Unbiased Cluster Survey research team. The goal was to search for objects varying in observed brightness over time, known as transients. They identified 14 such transients across the field of view. 12 of those transients were located in 3 galaxies that are highly magnified by gravitational lensing and are likely to be individual stars or multiple star systems that are briefly very highly magnified. The remaining 2 transients are within more moderately magnified background galaxies and are likely to be supernovae. We're calling MACS 0416 the Christmas Tree Galaxy Cluster, both because it's so colorful and because of these flickering lights we find within it. We can see transients everywhere, said Haojing Yan of the University of Missouri in Columbia, lead author of one paper describing the scientific results. Finding so many transients with observations spanning a relatively short time frame suggests that astronomers could find many additional transients in this cluster, and others like it, through regular monitoring with Webb. Among the transients the team identified, one stood out in particular. Located in a galaxy that existed about 3 billion years after the Big Bang, it is magnified by a factor of at least 4,000. The team nicknamed the star system Mothra in a nod to its monster nature, being both extremely bright and extremely magnified. It joins another lensed star the researchers previously identified that they nicknamed Godzilla. Interestingly, Mothra is also visible in the Hubble observations that were taken 9 years previously. This is unusual because a very specific alignment between the foreground galaxy cluster and the background star is needed to magnify a star so greatly. The mutual motions of the star and the cluster should have eventually eliminated that alignment. The most likely explanation is that there is an additional object within the foreground cluster that is adding more magnification. The team was able to constrain its mass to be between 10,000 and 1 million times the mass of our Sun. However, the exact nature of this so-called millilens remains unknown. As José Diego of the Instituto de Física de Cantabria in Spain, lead author of the paper detailing the findings, stated, "The most likely explanation is a globular star cluster that's too faint for Webb to see directly. But we don't know the true nature of this additional lens yet." The Webb data shown here was obtained as part of Pearl's GTO, Program 1176. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.